We're really privileged to have John McCalpin join us. And he's going to review the history of the changing balance between computation, memory, latency, and bandwidth, a topic that's been with us for a very long time. And fortunately, John has experienced it from many different dimensions and perspectives. He's currently a research scientist in the High Performance Computing Group and the co-director of the Advanced Computational Laboratory, the ACE Lab, at the University of Texas at Austin, in particular at the Texas Advanced Computing Consortium. And John really has a vast history. He joined TAC in 2009. But he has 12 years of experience in performance analysis and system architecture, really beginning with the SGI, the Origin 2000. He also worked at IBM on the PERCS Power 7, the prototype that was done through the PERCS program. And really covers all the bases by having an oceanography degree and really starting out in ocean modeling. So really a comprehensive perspective in history. Thanks, John.
Thank you very much. It's a great pleasure to be here today. I think we've got the monitors set so that I can see my notes. I was able to click through all of the slides in 55 seconds in the hotel room, so I shouldn't have any trouble finishing the talk. Today's talk is going to be a little more technical, mostly three parts. First, I'm going to talk about the changes in the system architectures and system sizes that I've observed through my own analysis of the top 500 lists that Jack Dongarra has kept since 1993. Then I'll talk about some of the underlying semiconductor technology changes that have sort of led to the different availability of machines that then led to the choices that people made, and talk about how those technology changes led to a different user performance experience and the implications of that. And finally, give a few speculations. First, the sort of business as usual straight line projection of what we can expect to happen based on current technology changes, and then give you some ideas of alternate approaches that I think could bring us to a faster rate of increase of delivered performance. So the top 500 list of systems is it's a useful piece of data. It's not unambiguous. Not all of the machines in the top 500 list are actually used for high performance computing, and not all machines used in high performance computing are on the top 500 list. I know that at one point I got a significant bonus from IBM for finding out how to get a lot of commercial database machines onto the list. And I know that that's happened in a number of areas. That's less true recently than it was at that time, just because of the sizes of the machines. So what I've done here for this first description is the percentage of the total performance, the aggregate performance of the 500 systems that has been delivered by machines of different types over the past 20 years. And we start in the 1993 when Jack Dongarra started the top 500 list. More than 50% of the performance in the list was still from the vector supercomputers, Cray and CDC vector supercomputers, although it was clearly dropping rapidly at that point. The little blip In 2002 was not a little blip, a very large machine, the Earth Simulator in Japan, which was a cluster of a large number of vector machines. But that didn't indicate a resurgence in the popularity of the architecture. It was a large one-time expense, and those faded out. So what was replacing the vector machines in the mid-1990s were the RISC microprocessor-based systems. In about 1990, the phrase, the attack of the killer micros, was popular. And this is when I was beginning my faculty work in ocean modeling. On some applications, these killer micros gave performance that was remarkably close to the performance of the big vector supercomputers. On my applications, it was not close, and that we'll talk a little bit more about how that led to my own career path. The blip there at the in 2011 in the RISC processors is the K machine in Japan, which is based on a Spark processor developed by Fujitsu. I don't have time to go into it, but there are 7 different important RISC processor families that traded places and exchanged market share very rapidly during this period. Starting in the early first decade of the 2000s, the blue indicates the contribution from x86-based systems. The first was ASCII Red in 1997, which was a machine built out of 32-bit processors. You see the big boost around 2004, 2005, and it's not that there was a single giant machine. By 2004, for example, 4 of the top 10 machines in the top 500 list were x86 clusters. A few of them 32-bit, but fairly quickly transitioning to the 64-bit architectures, both from AMD and from Intel. The yellow category is what I refer to as MPPs. I use a different categorization than you will find in the top 500 website and their presentations. From my perspective, an MPP is a machine for which the development cost of the most expensive component had to be covered by the high-end supercomputing market. There wasn't any mass volume associated with this. So so we end up with different categories. The big players in here, IBM Blue Gene L in the early 2000s was a machine that was specifically built for significant large-scale applications. It was quite successful. The Blue Gene Q showed a big contribution in the 2012 era. And then Taihu Lite, the fastest machine in the world that was announced in the June top 500 list, is also in this category and increased the bulge there. And this final category is accelerated systems. These were introduced with great fanfare a few years ago, and it was not clear to anyone whether or not they were going to take over the world. The first of the big accelerated machines was the Roadrunner machine at Los Alamos. And it was effectively the only large accelerated machine using the IBM Cell processor. The big bump in 2013-ish was the Tianhe 2 system accelerated with first-generation Intel Xeon Phi processors. But what's interesting to me about this is that the fraction of performance that came from accelerated systems peaked at about 30% and has been decreasing. It's under 20% of the list at this point if you subtract out the portion of the performance that comes from x86 processors. And the number of systems on the list that are accelerated has never been more than 20% and is currently around 15%. A little note here. It's hard to reverse engineer how much of the performance of these systems comes from the x86 processors, how much from the accelerators. But what the overall lesson is that in the most recent list, which was released Monday morning, x86 systems without accelerators account for about 55% of the performance of all of the machines on the list. And if you include the x86 contribution from the accelerated machines, we're up over 60%. So we've seen in these pictures some large changes in what people buy. And why did that happen? Well, it comes down to money. This is a little more high-level cartoonish view. In the 1980s, a supercomputer was pretty much $1.5 million a processor. And so the only options were institution-wide or nationally shared machines. And the prices on those machines did not come down very much. In the early 1990s, a one processor machine was $1.5 million, and a 32 processor machine was $32 million. The RISC processors came in at prices as high as $50,000 a processor, sometimes somewhat lower than that. So you had about a 20-to-1 reduction in price. And that led to the disruptive technology where the cheaper technology is not as good, but it addresses a much larger market. That allows it to bring in more revenue. It's on a technology base that is able to turn technology generations more rapidly. Then in the early 2000s, there was another large shift in price to multi-core or to x86, mostly dual socket x86 platforms. What's interesting about this to me is that the price per socket has not changed in 10 years. It's gone from maybe $3,500 a socket in 2004. It dropped a little bit, and then the multi-cores started getting bigger and the prices started going up. The price per core continues to drop, but it's not dropping very fast, as you can see on the very bottom curve there. So the consequence of these technology transitions has a huge influence on the number of processors you have to deal with. In the early lists, the vector machines had 4 processors, average, and by the late 90s, maybe 32 processors. They were replaced by RISC machines with hundreds of processors, up to 1,000, then by x86 machines. In the latest top 500 list, the average core count of an x86 non-accelerated system is 48,000 cores. This changes the model. When I started doing supercomputing, there were a whole lot more users than cores, and my allocation was 1 hour of CPU time on a cray per day. And so there was absolutely no reason to be interested in parallelism. It was only when my allocation became more than significantly more than order 10 cores for every hour of the day that I really had to start worrying about it. And now we're at the point where without parallelism, you can't get the work done. Let me make a brief comment about heterogeneous systems. More and more sites are building clusters of clusters, and I think this is a good thing. There's a PR value in building a large homogeneous supercomputer that you can run a single benchmark on and say, gee whiz, we're the best. But different applications have different requirements, so many sites target the majority of their budget toward 2-socket machines with small nodes, and then spend smaller amount of the budget on large memory or accelerated nodes. And that's consistent with what we've seen on the list of a partial shift to accelerated systems that doesn't seem to be increasing. So let me talk a little bit, before I talk about the technology trends, I want to say a little bit about where I got to this point. which is something called the stream benchmark. In 1991, I was on the faculty at the University of Delaware doing my ocean modeling, and the killer micros came out, and they didn't work very well for me. So I created this code that I intended to be an extremely simplified representation of the kinds of operations that I was doing in my ocean models. And it ended up being a good combination of free and easy, and easy to understand, easy to modify, and has been widely used since that time, still widely used. I will occasionally get email from China, from manufacturers who are using it in manufacturing test at the end of their assembly line, and they say, I don't understand this stream benchmark number, can you help me? And those are interesting conversations. We have about 1,100 results in the main database, which is held at the University of Virginia. I've never been to the University of Virginia, but when I left academia for industry in 1996, they agreed to host the benchmark to keep it out of the grubby hands of industry. So what the stream benchmark consists of is 4 kernels, each of which separately timed. There's just copying one array to another, multiplying, adding 2 arrays, and then an add with a scale operation. One thing to note about these 4 kernels in this form is that each kernel feeds into the next one. So the left-hand side of one kernel is one of the right-hand side operands. The very first versions of the stream benchmark did not have this property, and compilers would sometimes notice that I wasn't using the results, and they would delete all of the calculations, and you would get infinite performance. Fortunately, stream is one of those things that's easy enough to understand that claiming infinite performance is not going to get you very far. But the current code has been stable for a long time. The benchmark requires a little configuration. The size that is used is chosen to make each one of the arrays much larger than the cache memory that's available on the machine, so that when you do the loads and stores, you can expect them to come from the main memory. I repeat it 10 times, I take the best time. Now, I'm measuring execution time. I'm not measuring bandwidth. So if I'm claiming bandwidth, I need to figure out how to convert it. And the way I do that is by assuming that all of the data must be coming from memory because it's much too big to be contained by the cache. But I make specific choices about how many bytes I count for each one of these iterations. And I count reads and writes. It turns out there's 3 different ways to count bytes for that first copy operation. The people who do bcopy benchmarking only count the size of the source block. So they would count 8 bytes, but I count also the amount that's written. In many computers, the processor will, if you write to a data item that's not in a cache, it'll read it from memory before overwriting the data, and that is very helpful for maintaining cache coherence. It's not required. If a processor does that, I don't give them any credit for it. And so if you're trying to understand it at the hardware level, you do need to know whether your processor is doing these write allocates or not. So I have this benchmark that represents my some aspects of my ocean models. After looking at results for a while, I started thinking about what I call system balances. And this is a model of performance in which I think about performance as orthogonal components. And examples are the peak arithmetic performance as you try to estimate or with a LinPack benchmark, the sustained memory bandwidth that you get from the stream benchmark. Sometimes you need to include a memory latency component, which I'll talk about a little bit more. And then now that most machines are clusters, we have interconnect bandwidth, interconnect latency. I won't talk about those much today. But the system balances are the ratios of these, and I'll work through some examples. Before I get to the examples, each of these speeds or rates are advancing at different rates due to the underlying technology and due to the choices people make about what they want to purchase. Right in the recent era, the peak computational rate per socket is increasing at 50 to 60% per year. The memory bandwidth is increasing at 20, 25% per year. So there's a divergence. The memory latency is actually increasing recently. Note that's in red because that's the wrong direction. You want memory latency to go down, and it's not, it's going up. The interconnect bandwidth is increasing slowly. The interconnect latency is improving slowly. And since these are ratios of per year changes over 5, 10 years, you expect these to make very large differences in the balance of the machine, whether or not an application is limited by the arithmetic capability of the computer or limited by the ability of the computer to move data around. So this first example is what I usually call the stream balance, and my units are a little bit different than other people use. It's the peak arithmetic rate divided by the sustained memory bandwidth in words, where the word size is usually 64 bits if I'm using 64-bit arithmetic. The sort of, in the early 1990s, the systems were configured such that a memory reference cost as much as a few arithmetic operations, 2 or 8. By 2005, it was about 10, and we are now sitting at a ratio of about 100. And what that means is that if you're doing arithmetic and streaming data from memory, so this is friendly memory access patterns, streaming contiguous data, every one of those references takes as much time as 100 floating point operations. And the maximum utilization you're going to get is going to be under 1%. If you look at the full stream database, you'll see a whole lot more data than this. I have to admit, these are selected systems. But I believe they're reasonably selected. They were chosen because they were commercially successful, which means they didn't cost too much. They were well balanced. People liked to use them. Starting at 2005, the data points are a single core Opteron, and then a dual core Opteron, and then a dual core Opteron with DDR2 memory. The next 4 points are Intel, Westmere, Sandy Bridge, Ivy Bridge, and Haswell processors. The last point that's hatched out there is my speculation for a future Intel processor that may show up next year. But this is all sort of depressing because in physics, when you have an algorithm, the amount of work that you need to do for every data element that you bring in from memory is usually fixed. It doesn't change over time, and yet the way the systems are going up, if you want to use the system, you have to do more and more work on each data item. So this is, it looks bad, but there's a lot of white space in the chart above that, and that's because every other metric is much, much worse. The memory latency, in the case where you can't prefetch the data or you don't use all of the data that you bring in a cache line, is getting worse at a significantly faster rate. At this point in 2016, if a single core on a high-end Intel processor, say a Haswell Broadwell processor, if a single core misses the cache and has to wait for memory, you've lost the ability to do 4,000 floating point operations. That number's going up over time. as the arithmetic rates are improving. And that means that it doesn't take very many unpredictable memory references that can't be fetched to start really eating into the efficiency of your job. Interconnect bandwidth is similar. Interconnect latency, I had to add 3 more orders of magnitude on top of the chart because the numbers are so huge. The top line corresponds to a typical hybrid programming model in which you've got a master thread, a single MPI task with many threads, 1 per core, and the MPI task experiences a full memory latency while all the other cores are waiting for it. So that's about 2 million floating point operations for one network latency. So you can recover some of this by solving larger problems, but these are very, very stiff, difficult problems. Even a decade ago, it was a factor of 100 better. So this is painful. So there's a lot of interest now in accelerators and ManyCore. I wanted to do a quick comparison of the balance of 2012 and 2016 products. The left 3 columns are, the blue is a Xeon E5 2680, 90, 80, 2680. In our Stampede system, has a balance of around 40 floating point operations per word of memory traffic. A little high. The Xeon Phi first generation, Knight's Corner, has a similar balance, and the NVIDIA K20X, also from the same time frame, has a similar balance. And this is what I'm kind of trying to say is that the technology is sort of the same on these things, and they're often, for example, the Xeon Phi and the NVIDIA K20X both use GDDR5 graphics memory to keep the bandwidth up high enough so that it's not completely unbalanced compared to the Xeon processor. Then in 2016, we start to see some changes. Broadwell processors that were announced early this year have increased the memory bandwidth by about 50%, but have tripled the peak floating point performance. So the balance parameter is up around 80 floating point operations per word. The second generation Xeon Phi has already given up on GDDR5 memory and has gone to a stacked memory that they call MCDRAM in order to maintain a similar balance. And then the new NVIDIA P100 system has also gone to a slightly different stacked memory to try to keep the performance up. But again, the peak flops have gone up faster than the memory bandwidth has gone up. So the amount of work that you need to do for each memory reference gets higher and higher over time. So why are flops increasing so fast? Why can mean a couple of different things, but what are the technological components of that? It's the product of the frequency, the number of floating point operations per cycle per core, and the number of cores. And these are driven at different levels. Here I'm just looking at Intel processors. Because these are multiplicative factors, this is a log graph. So the bottom is 1 gigaflop per package. The 1.0 is 10 gigaflops per package, then 100, then 1,000 gigaflops per package. So in the early 2000s, the Pentiums were running at about 3 gigahertz and could do 2 operations per cycle on 1 core, 6.4 gigaflops per package. Core 2 doubled the number of floating point operations per cycle and doubled the number of cores with a slight frequency drop. Nehalem and Westmere mostly increased the core count. Sandy Bridge and Ivy Bridge doubled the peak performance again and increased the core count. There's some evidence that the frequencies might be sliding a little bit. The Haswell-Broadwell, the frequencies are definitely sliding. The core counts are going up. They've doubled the floating point operations per cycle again. And you're now in the 10-year period from 2005 to 2015, we've gone from 6 gigaflops per socket to 400. So this is a very impressive rate of increase of peak performance. And this is some estimates of what the next generation will be. Intel has disclosed that they're doubling the peak performance again. I'm guessing on the core counts and frequencies. But we're looking at over a teraflop per chip peak performance. Now, those were all mainstream processors. This is looking at a comparison of mainstream and ManyCore processors. For the 2012 era products, you see on the left is the Sandy Bridge processor at 3 gigahertz, doing with 8 cores, doing 8 operations per cycle. The ManyCore Xeon Phi first generation had a third of the frequency and 7 times as many cores and twice as many operations per cycle, to give a total of a 5x higher floating point operations per package. They were able to do that in large part because frequency reduction allows significant power reduction. And so more slow processors enables you to deliver more peak performance in the same power envelope. And then in 2016, we have a similar comparison. We're now at about 14 cores on a Xeon at 16 floating point operations. The frequency difference has diminished a little bit. It's less than 2x instead of almost 3x. And now the second generation Xeon Phi Knights Landing has about almost 7 times the peak performance of a Broadwell processor. So that's the story of the flops. Why are we not getting memory bandwidth? First, there's been a fairly slow rate of pin speed improvements. This is wires that go between chips that are governed by different physics than wires that are on chips, and they don't get faster when the transistors get faster. Certainly, the emphasis in the DRAM industry has been on increasing the capacity and not improving the bandwidth. There's also the problem that the shared bus architecture that's used to allow multiple DIMMs per channel is extremely painful to try to run faster. Another interesting factor is that the DRAM cycle time is really almost unchanged in 20 years. Maybe a factor of 2 in 20 years. And so if you want to increase the external rate while the internal rate is the same, the only way you can do that is to fetch larger and larger blocks internally and then send them out as longer and longer bursts on the external interface. Right now, we're already up to a 64-byte minimum transfer, and so any improvements in performance require sending where the smallest memory access is more than a cache line, and that becomes inconvenient. And there's also a reluctance to add more channels. We've had 1 channel per chip in the early 2000s, 2 channels per chip in the 2004 era, and then they went to 3 in 2008 and 4. We're still at 4 in the mainstream processors because those pins cost money. So memory latency is even more problematic than bandwidth. One reason that memory latency is not improving is that there are more levels in the cache hierarchy. The sort of standard system now is level 1 cache, level 2 private cache, level 3 shared cache, and then memory. And the lookups in those caches are typically serialized to save power. So when you add another level of cache, you extend the time before you've even asked the memory for the data. Another issue which I think is not as well understood is that there are a whole lot of asynchronous clock boundaries in a chip. In the past, when a chip was a more monolithic thing, you'd have a processor and it would talk at a bus frequency that was usually in a careful fixed relationship with the CPU clock to a memory controller. But in order to save power, there are now many, many different frequency domains on modern chips. Every time you cross from one frequency domain to another, it's an asynchronous transition that adds latency, and it's quite difficult to make these efficient, especially in the case where you're not sure which of the two sides is going to be faster at any given time, because sometimes the ring is faster than the core, sometimes it's slower than the core, and you do have to go through these in both directions. So a typical transaction, if you miss your caches, requires 6 asynchronous boundary crossings in order to get the snoop response. And there's more cores on each chip. I remember at AMD when we came out with the 2-core processors, we started thinking, is anybody going to be able to use more than 8 cores? And what are we going to do when we get to that point? It's now at the point where it's clear from looking at recent Intel products that it's getting challenging to maintain cache coherence even within a single chip. There are now modes of operation where they take a single chip and divide it into 2 to reduce the coherence traffic. Right now, in 2-socket systems, the memory latency is typically dominated by the time required to verify that the caches in the other chip don't have the data. Local performance and the number of cores that you have will increase that. And then the frequencies are coming down. They were well into the 3s and now are coming down. So you have to do you have to do this extra work and you have to do it slower. Interconnect bandwidth is mostly the same issue of pin speed improvements, and nobody wants to put more channels on there. If you put more channels on there, you get fewer ports per switch, or you have to buy more switches, and nobody wants to buy things. Interconnect latency, I kept this in there because I wanted to make this point. Interconnect latency is improving slowly in large part because of a legacy I/O architecture that was designed around disks. The architecture of machines was not designed around communication that can happen in hundreds of nanoseconds. And this is sort of ubiquitous in the industry. There's also tends to be a mismatch between the software requirements and the hardware capabilities, particularly things like MPI tag matching. So a different implication of these, not just a balance issue, is the issue of concurrency. So I'd like to thank Burton Smith here for getting me started thinking about this some decades ago. Little's law from queuing theory says that the concurrency required in a channel is equal to the latency times the bandwidth. And what we have in computing systems right now is the latency is constant and the bandwidth is going up. And that means that you have to have more and more transactions in the channel. I had to go back to a 2005 era system to build a picture that sort of demonstrated this pipelining. In this particular system, had a 60 nanosecond latency, and it takes 10 nanoseconds to move a cache line. And so you have to have 6 cache lines in the process of being fetched in order to keep the data bus in green busy at every cycle. In 2005, you could do that with 1 core. 1 core could handle 8 outstanding cache misses, and so 6 was okay. This picture probably needs larger text. I'll tell you a little bit about what it is. What I've done is I've calculated the latency times the bandwidth on the same set of representative machines I used on the earlier slides, and divided it into 64 byte units because that's the most common cache line size. And what you see in the middle around the 2005 era is the Opteron that could handle this with 1 processor. Still not too bad in 2008. By the time you get to 2012, you're up at 30 cache lines per chip. Now you're at about 100 cache lines per chip. And one core can still only have 10 outstanding cache misses. And this is where you get into some of the big problems. Architectures are not built, they weren't designed around a multi-level hierarchy. They were designed around a flat memory system where you just load things and they show up. And sometimes a cache and a prefetch would be helpful, but it wasn't really a big deal. Implementations also have limited support for the number of cache misses they can support. And L2 prefetchers help, but you can't control them. And things that are not controllable tend to be complicated, hard to understand, and energy expensive. So right now, if you have a code that's bandwidth limited, you actually need to use most of the cores not to do the arithmetic, but to generate the cache misses. And this is a very inefficient way of using the hardware. And it requires complex buffers to reorder the operations, and that takes a lot of money to design, which means you have to charge a lot for the chips, and it costs a lot of power to organize. It also hurts when you get to the DRAM. One thing that we're finding now is that in order to get enough bandwidth, we now need to purchase more memory than we actually need for the machine, because the memory chips are getting bigger, but their bandwidth is not going up. I've alluded to some power and energy issues. One important point that I wanted to make right now, power density is definitely important in building and designing chips. And bulk power is an issue. Power is absolutely not a first order concern in operating cost. And I think sometimes the funding programs get a little bit over enthusiastic about some ideas. Given the static prices of nodes over the past decade, most HPC-oriented configurations, power and cooling costs is only 5 to 7% of the original purchase price per year. Later, if processors become much cheaper, then it will be potentially more important. For example, you could use client processors that are less expensive, use the same cores, but a significant fraction of the energy. When you go into the embedded space, maybe this sometimes becomes more serious. A $5 processor that uses 5 watts will cost $7 a year for power and cooling. And that's fine if you have one of them in your iPhone, because the iPhone costs $700. If you buy 5 million of them to be your HPC system for $25 million, then you're stuck with a $35 million a year electric bill, and that's not going to work. So final comments, what does this mean? The most important lesson, maybe, I don't know, most. One thing that's very important, I don't want people to misunderstand. I come from the high bandwidth side of the world, so I talk about high bandwidth, but high bandwidth is not the only application area. Applications have huge range. This is an example of a time breakdown of CPU time in green, memory latency time in red, and memory bandwidth time in blue from the Spec CPU 2006 applications on a 2006 era system. And there are clearly applications over there that are 99% CPU bound, and they still are. But one in the middle that I know a lot about, the WRF Weather Research Forecast Code, in the 2006 era system was 68% CPU time and 30% memory time. And now on a modern processor is about 70% memory time and only 30% CPU time. So we're seeing a significant shift of applications that used to be compute bound that are now memory bandwidth bound. And it changes, understanding this changes your thought process on what processors you're going to buy, whether you're going to go for all of the cores, whether you're going to go for the high frequencies. another issue which I alluded to earlier is that if your workload is heterogeneous, then a homogeneous system is almost certainly not the right answer. And people are getting better about this, but we still, when we go in and configure machines, we do need to think about the blocks of applications and their characteristics and try to target subclusters that are appropriate for each of those. Sometimes I'll see people say things like optimized for general purpose workloads, and that doesn't mean anything. It means I didn't think about it very much. So in the short term, here's what we're going to see. We're going to see more flops and not much more bandwidth. So if you want to follow the performance curve that's improving the most rapidly, you have to figure out how to get more arithmetic into your applications for every memory reference in every generation. Some applications will naturally be able to exploit this and some won't. And there are some short-term things that you can do, increasing computational intensity, and but others are going to be advancing in performance at the slower technology rates. Okay, I think I'll stop here. It's getting more complicated over time, keeps us employed, but in the short term, what we have to do is exploit all sorts of different kinds of parallelism, node level, core level, SIMD, and we have to figure out how to increase data reuse. I hope that there are breakthrough technologies. I have some ideas. I'd be happy to talk to people afterwards, but I think that's the talk for today.
Thanks, John. I think we're really, just to keep on schedule, we're out of time, but I would encourage people to stay after and ask John and thank him again for that very comprehensive look at performance and balance systems and how it translates to applications.
All right.
Thank you, John.